Okay, today we are going to take a look at Chapter 4 on determinants. This is a brand new chapter. Basically, a determinant is a topic that might be familiar to some of you. You might have seen this somewhere, but it's probably going to be new for some of you. And our purpose for looking at determinants is that they're going to help us to calculate eigenvalues in the next chapter, which is an important topic for our course. And we'll do this in stages, starting with the determinant of a 2 by 2 matrix. Okay, so if you look at the definition, and this is page 87 of the workbook that we're looking at, the way that we calculate a 2 by 2 determinant is basically just to look at the entries on the main diagonal and multiply them together, and then to subtract the entries on the off diagonal. So that's going to give us AD minus BC, and that scalar is the way that we're going to define the determinant of a 2 by 2 matrix. Okay, you might also notice with this definition, we've got two kind of notational ways of representing a determinant. We can write it either DET of A, okay, or we can use the bar notation. Both of those symbols represent determinant. Okay, so that said, let's calculate a couple of 2 by 2 determinants together. Okay, so starting with A here, if we apply that formula that we just talked about, the determinant of this would be 3 times 2, there's the main diagonal entries, minus 0 times 0, there are the off diagonal entries, and so we're going to get a result of 6, which is our determinant. Okay, now what's kind of interesting here is that there's a geometric interpretation to the determinant which we can get if we look at the columns of our matrix, 3, 0, and 0, 2. I'm going to give those two vectors names. Okay, let's call U the first column and V the second column. And if we plot those two vectors, okay, just in the ordinary two-dimensional plane here, U would be this vector, and V would be that vector. Okay, and if you think of the rectangle that those two vectors form, notice that the number 6 that we got is just the area of that rectangle. That's a 3 by 2 rectangle that we just drew. Okay, so the shaded area actually equals our determinant. Okay, let's take a look at the second matrix in part B and see if we can calculate its determinant. Okay, same process as before. Okay, so starting from our matrix, we're going to take 2 times negative 1, those are the main diagonal entries, minus 1 times 1, the off diagonal entries. This time, if you do the arithmetic, minus 2 minus 1 is negative 3, and so negative 3 is our determinant. Okay, and this also has a similar geometric interpretation. Okay, if we think of the columns again as being two vectors, okay, this time we'll let U be the first column, 2, 1. Okay, and V will be the second one, 1, negative 1. Okay, let's scroll up just a little bit here. Okay, and if we draw another picture, okay, our vector 2, 1, well, let's just plot ourselves. Make ourselves a little scale here. Okay, so 2, 1 would be the vector that's kind of up here. Okay, so there's U. And 1, negative 1 would be down here. Okay, there's V. And this time, we can't make a rectangle, but we can make a parallelogram, kind of determined by those two vectors. Okay, and it would look like this. Okay, and it turns out that the area there would actually be 3. It's not as easy to figure out as it was in the previous one, but we could use a little geometry. And the shaded area equals 3, which is the absolute value of our determinant. Okay, so for 2 by 2 matrices, the determinant, the absolute value of the determinant, that is, always represents an area.